Welcome to our class today as we continue with our study on building and verifying proofs in Noir. So this time we'll be looking at how to build and verify Merkle proofs in Noir. So Merkle proofs is why Merkle proofs, or what is it before even why? So Merkle proofs let us, or Merkle trees, let me begin by Merkle trees. They let us to prove that a specific item is part of a larger data set without revealing the entire data set. So supposing you just want to prove that something is part of this group and you don't want to reveal the entire group. So what we then use is what we call Merkle tree. So that is what we'll be doing, and therefore that proof is what we call Merkle proof. So that is what we'll be looking at today, and of course we may not exhaust it today, but the thing is we will introduce it and then proceed with it in the subsequent classes. So the goal of our today's class is we need to understand what Merkle trees are, and then how to use them in Noir circuits. That is very important. How do we use them? Because we'll be writing Noir circuits. After you've written your Noir circuit, how do you use Merkle tree? How do you use them? Then explore privacy benefits of Merkle trees. Of course, I've said you just want to prove that a point A is part of as a data set, but you don't want to reveal the entire data set. So that is what we'll be doing in our class. And that's what I've said. That answers our question here. The question is, what is a Merkle tree? And I've said a Merkle tree is a way to securely summarize a large data set of data using trees or trees of hashes. Now, so this tree has leaves, and each leaf node is a hash of some data, e.g. an address. We are talking about if the leaf will be the address. That's what you want to prove. That was you want to prove. So we have this tree, and the tree has the leaves. Now we don't want to reveal the other leaves. We're interested about this one leaf, and we want to show that it's part of this data set. It's part of this set without revealing what is in the set, the other elements of the set, and so on. So it could just be an address and so on. Now, each parent node is a hash of its children. So the children will be we shall have, if this is a parent, we have the children and so on. And this child will also have some other children and so on until we reach the leaf, the leaf. So it's this leaf that we want to prove that it's part of this tree. So at the top of the tree, then it's the root. That is the root, and then from there we come to the branches as we proceed to the leaf, the specific leaf. Now I've drawn something just to illustrate that. I think it's clear, you can see it. So you have the root, that is the root, and then we have this child and this child. The other children out of this. So H1 has these two, H2 has these two, but now these are what we call the leaves. These are the leaves. So we have leaf H1 I believe H2, H3. So we want to prove that this leaf is part of this set without revealing the other sets, the other elements of the set. That's what we will be looking at. So this is just a tree, what we call the Merkle tree, and that is what it will be helping us to do. So we'll be writing proofs using Merkle tree. And so what is important, how do we then write this circuit using Merkle? So I'll show you how to write circuit, but of course, we've already known how to write circuits and make elements private, others public in Noir. So that is the same knowledge you'll be using in our today's class. Now, why do we use Merkle trees? Why do we use Merkle trees? Because somebody will say, why can't we just write this and make this private, make this public, and so that the one that is private is hidden from the verifier. It's only the prover who knows, the verifier does not know. So it's a secret. But we have to bring in Merkle trees because of one, efficiency. So prove inclusion of one item in a big set with a short proof. So it's not a very long proof, it's just a short proof. And we are proving inclusion. We are proving inclusion of one item. So we are proving that there's one item inside this set. But we are using a very short proof. So efficiency of the proof. That is one point as to why we are using Merkle tree. Because we are saying that it's possible you can write a proof and prove that a set has some point. A point A is included in that set, for instance, or prove inclusion. But what about efficiency? Those proofs without Merkle tree may not be efficient. So that is why Merkle trees come in. And also come in because of privacy, what you've just talked about, because we don't want to reveal the entire set or the entire list. We only want to prove that an item is inside that list. That is the only thing we want to prove. So we don't want to give the entire set. We don't want the entire set to be known. We only want it to be known that there's a particular item inside that list. So that is what we call privacy. And that is why Merkle trees come in, Merkle proofs. Well, it's also blockchain friendly. And that is why it's used in airdrops, in whitelists, voting, and more other things that require privacy, many other issues that require privacy. This just a few: airdrops, whitelist, and so on, voting, and so on. They require privacy, but we have so many others that require privacy. Therefore, Merkle tree will be applied in all of those. So it's just upon you to see how to write your circuits using Merkle tree and ensure that there's privacy. That is the only thing we need to know. Since some of these circuits, once we've learned how to write one, we can always apply the same knowledge to write the other. For instance, when you talk about privacy, it's just the same thing. Just the same thing, you're just applying it in different scenarios. So just make a few amendments here and there, but the tactic remains the same. So it's just, you just learn one. Once you've learned one, it's on you now to try and see how do you apply this knowledge in other areas? If you, for instance, supposing you learned how to do it, how to write a Merkle proof in voting to ensure that there's privacy in voting, then you can apply that knowledge in something else and ensure privacy. So Merkle proofs, what we'll be doing is this. We'll be proving that your item is in the tree. So for you to do that, because you want to show that this item is in the tree or this element is in that set, what you will do, you will show your data. That is, you will show the leaf. You want to show the leaf, and then you show the hashes of siblings along the path to the root. That is the only thing you'll show, the hashes. You remember the diagram I showed? There were hashes and so on. So the verifier can recompute the root and check it matches with the official value. So that is what the verifier will be doing, because the verifier will not get to know the leaf. Remember, the leaf is what we want to show is part of a set, and we don't want to reveal other members of the set. So the prover knows, is only the prover who knows what the leaf is. And the prover may even also be knowing, he may also be knowing these members of the set. But now it's the verifier we are hiding this information from. But this verifier can recompute. Of course, there'll be some other public information accessible to this verifier. So using that, this guy can recompute the root and check if it matches with official value. So that is official value means the public value that is accessible to this verifier. Now, so Merkle trees can be done in various languages, even in Rust, but our intention is to do them, to do Merkle proofs in Noir. That is our intention. So therefore, we'll be looking at how do we do it in Noir. Just a repeat of what we've already said. Merkle proofs will let you to prove that a particular value. And for example, when you talk about a particular value, you're talking about your address, for instance. You want to prove that your address is part of the set. And the set here will be the whitelist or the airdrop list. So supposing there was airdrop list, you don't want to reveal what it is, but you just want to show that your address was part of that list, was in that list. So what you do, you provide the path of hashes from your value up to the root. You just provide the hashes, the path of the hashes from the leaf. So that path from the leaf all the way to the root, you provide the path, but you're not revealing the members inside. So that is where zero knowledge comes in. Zero knowledge circuits. And these are just circuits, as I mentioned earlier, like those we've been writing in Noir. So we just privacy and so on. But the circuits we've been writing. Now, how are they designed? That is they can be that your belief is a private input. So that is writing a circuit. I remember we said you use the word pub if the field is public, you use the word pub. But if it's private, you just write it, but then you do not indicate the word pub. So you just leave it the way it is, and then it's understood to be private. But when you write the word pub here, then it's also understood that that field is public and therefore it's accessible to the prover, not the verifier. The verifier can access it. The public knows it. So that means it's not a secret. But what you want to be a secret, like the leaf, you would then make it private. That is what brings in zero knowledge proof. So you make it private. There's no word pub coming before it. No, after it coming. No, it's before it. There's no word pub before it. So if you want privacy, that is what I mean. If you want privacy, you structure your Noir circuit as we've been doing, such that the circuit verifies that I know a value that is a member of this Merkle tree with its root, and I know the Merkle proof path. It's also the structure such that, but the proof does not reveal, it should be structured so that the proof does not reveal the value. It does not reveal the leaf. So you're just saying that I know a value that is part of the Merkle tree. And I know the proof, the Merkle proof tree path. You remember the path of hashes that we talked about. So you know the Merkle tree, you know that this value is part of the Merkle tree, and you know the proof. But then the proof should not be one that reveals the value. And so to the verifier, all they see is a valid proof. The verifier will just be saying that this proof is valid, but they'll not be saying the leaf. So this is then what we call private set membership. Private set membership. So we're just proving that private leaf, by private, I mean that you've not indicated the word public. You've not indicated the word public. So by private, I mean it's only known to the prover. The verifier does not know it. So that is private set membership. So what I've said earlier, and I repeat, is that once you now write this private set membership proof, for one, you can always apply it in another scenario and write it because the way it's reasoned is just the same way. It's not complicated. So you can write it for anonymous voting, you can write it for private airdrops and so on. So what will you be doing in anonymous voting? Anonymous voting, the proof that we'll be writing will be that you can prove you are eligible to vote. That is just an example. You want to prove that you're eligible to vote. What that means, for instance, your ID number. You want to prove that your ID number is in the list of the voters. The list of the voters. but you don't want to reveal the ID number. So you don't want to reveal that. But you want to confirm to the verifier that your name or your ID is on the list without revealing the ID. So that's one thing you'll be doing in anonymous voting. You can write your code such that it does that. It's not the only thing you can do here. You can write so many other things about voting. You can also be writing about airdrops. So supposing you claim an airdrop, you just want to prove your address is eligible for the airdrop. But you don't want to expose your address. So you used address A, and now your address A has won an airdrop. So you just want to prove that this address is eligible for that airdrop, but you don't want to reveal your address. So once you know how to write it in anonymous voting, then you can write it here, you can write it somewhere else that requires privacy and so on. So that is how we do it, that you want to learn just in one way and apply it in another way. Now, these are the key points. I just repeat to emphasize how you achieve privacy. If your circuit makes the leaf value private value, then your membership will be secret. That's why I'm saying that when you're writing your fields, the one that indicate public, this is known to the public. The prover knows it. The prover knows it. Now the verifier knows it. But the one that has no pub, these are secret. Only the prover knows it. Only the prover. And so that is the key point number one. That this leaf you're writing, this leaf must not be known to the verifier, so it should not be public. But if the leaf is public, then it means that its membership is not secret, is revealed. So that is the only thing you need to know when you're writing this. And Noir helps us to do that you can indicate what value is public and which one is private. That's what Noir does. So I'll just be highlighting how do we then write a public Merkle tree proof that proves membership, set membership, and also private. But we are very much interested in the private bit because that is where our zero knowledge proof comes in, that we need to prove that a member is part of the set without revealing the set. And the member should not be known. The member should not be known. So the member, which is the leaf, must be private. But let's begin with the public, of course. This is just to mention so that you when you're writing and you're writing your circuit, you must know what do you want to keep private and what do you want to keep public, so that the one that you want to keep public, then what we want to discuss is how to keep it public. What we want to discuss is how to keep it public. The leaf, for the public proof, the leaf or the address is a public input to the circuit. So the verifier learns which member you are proving. So if you're proving, then the verifier, and you make it public, the verifier knows it. Now, this is used in cases where, this kind of proof is used in cases where it's okay for the prover to know which specific address is being claimed. For instance, that is just an example, where there's no problem the prover knowing, and then you use this public proof. This is the example. I'm not saying that this one may compile. It may not compile, but I just wanted to show you that look at this leaf. This is a public leaf. So if you're proving, then this one, the verifier knows it. The verifier knows this. Look at this root. This root is also public. So as I was saying, my intention for this example was just so in this case, the leaf is public. And the root is also public, you can see. And so the root is public, the leaf is public. So anyone verifying the proof will see the leaf you are proving. So you'll see the leaf, will know what the leaf is. It's not hidden from anybody. Now, apart from this public proof, we can also have private proof, and this is what we want. So in this case, the leaf value is made private. So the verifier sees only a valid proof. So the verifier is only able to tell that this proof is valid and that the Merkle tree, the Merkle root can also be seen by the verifier, the root. But the verifier will not know which leaf was used. Because you see, the tree has several leaves. So he's not able to know what leaf was used, but he's able to know the root because you're showing the root, the root to the root. So he's able to tell. So this one is what we use, therefore this proof is what we use in privacy preserving airdrops, is what we use in voting, is what we use in anonymous group membership, and so on. And so an example just to emphasize how it's written before we go to the real code. You can see this leaf as no word pub before it. And you can see that the root is public because the word pub comes before it. So I've said, therefore, in this example, only the root is public. This must be known, the root must be known, but the leaf must be concealed. So this circuit, therefore, will prove that I know a member of this set, but will not say what the member is, not reveal the member. I can just say I know the member of this group. It's not saying who the member of the group is. So I was just trying to give a full example of a Merkle tree proof that proves membership. And I'll be showing a code for that. I'll be showing, so it's therefore needless to show this. I'll be showing the code. Maybe it's important to just look through this this README that I had written for the private Merkle membership in our circuits. So the circuit above, although I'll be sharing it in my visual code, demonstrates Merkle set membership proof. So in it, you provide, you prove that you know a secret value that is a member of a specific Merkle tree. And then the proof does not reveal, the proof that you're using should not reveal which value or what leaf you know. Of course, it has that. This is what we always have in Nagotomil, and I'll be showing you how to write it, depending on the proof you're doing. So how it works is that you will provide the secret leaf. That is, a secret leaf, as we've said, is a value you want to prove in the secret set. So the set must also be secret. So you provide the proof, and the proof is the sibling hashes. Those are the roots from the root to, from the leaf to the root, the hashes. So those ones you provide. You provide the hashes from the leaf up to the root. The root, in the examples we've seen, the root has always been public. So you make it public. So that is what this verifier will be using. Because the verifier will be now tracing from the leaf to the root to see whether the proof is valid. But it does not know what leaf is. So you just provide something as a leaf, but and used. But can go through the proof and see that it's valid. Now, so what I'll do therefore at this point, I just want to share the code. Okay, let me begin with the dependencies of the nagotomil. This is just the normal thing that we've been seeing, writing nagotomil from when we began looking at Noir proofs and Noir circuits. Then I'll come to the nagotomil. This one, you don't want to struggle with it. I did not struggle with this one. In fact, you can even delete it and it generates automatically. So when I delete it and just come to this terminal and say nago check, this will help me come up with the nagotomil, certainly having to struggle with it. So if I just press enter, and if the circuit is okay, it runs, and it gives me the proof atomic. So the proof atomic, it's telling me that I should provide the index, I should provide the proof, I should provide the root, and I should provide the secret leaf. So these ones I'm putting in the the proof atomic. Remember that the verifier does not have access to this. What the verifier will be seeing is the proof that you generate from this when you compile. And let's come to the main.nr and see how short this proof is. Begins from here. This is the proof. Very short. Now, so you're using the partisan hash just to assist us in the hashing. Now look what the leaf, secret leaf. It's not private, it's not public, because we do not have any word public here. And then you have the proof. We have the index, which is a U32. And then we have the root. Then this is the program. This is, so for I in the range 0 to 3, remember that when you talk of 0 to 3, you are referring to 0, 1, 2. So in that range, we get the right. So what we are doing here, we're just defining the siblings until we go to the leaf. That's what we are doing. So remember the diagram I showed earlier. So if you're using that diagram, that's what we are doing here. So then what you are hashing are the two, those are the branches. As you move towards the leaf. So you're combining two, hash them together as you proceed to the leaf. Now, so for instance here, we hash the proof, and the proof is from I, as is the proof of I, which is a U32 element. Then of course you have to do the assertion. Assertion here is just to confirm that the hash to the root is correct. Just confirming that whatever is inside here is correct. So you must always have the assert. This is so that just confirm that what you run, the test, the main, what you are testing, the main function is correct. So that is what assert does. Then of course you can put some tests just to confirm the correctness of your proof. And the test, you begin with the hash, then test. Now you can always include a working test or even a failing test. And if it's a failing test, you must then indicate that this test would fail and this one would pass. So that is how we do it when you're writing a test. And when you go and check books and know book documentation, get to know very well how to write a test if it's failing, and how to write a test if it's not failing. So there are so many documentation that can always assist us in understanding how to write our circuit in Noir. So what I'm just referring to, let me just share something here. This is just documentation. Let's see. I'm trying to see how to share it because it's something online. How does somebody share something which is I don't know. Let me open it first of all. Does it mean I share the screen? You see. So I don't know whether you're seeing what I'm sharing. This is a documentation from Noir, and it's online. Let me minimize what is on my screen so that I have a few things on my screen so that I can easily see what I should share. It's this one. It's now okay. I'm not that one. The one I wanted to share is not that. Is this. Just to show you how to test, how we write tests in Noir. And that is how you're writing them, even in using Markle proof. So testing in Noir, this is just a documentation from Noir. Just write Noir and you get it. It's just https noirlang.org, and you get this documentation. I just come and click on tooling, and then it's up to testing in Noir. So what I just wanted to show you is that this is a test that will pass. These are tests that will pass. So you just write hash and then test, and then you write the test. And of course, you are doing by assert, using assert just to confirm that it's correct. Whatever comes out is correct. Now, if it is bound to fail, before that, of course, we run by Nago test. When you write Nago test, then it runs the tests. What about if the test is bound to fail? Now, if the test is to fail, if it's expected to fail, you write and you show by use of this hash tests. Let me just compare with what we saw in the test that passes. A test that passes is just this hash. Then those square brackets inside, you write test. But this one is the hash, then square brackets. Inside you write test, but then in brackets you say should fail. So that indicates that that test will fail. That's how you write it in Noir. That's how you write it in Noir, and that is how it's been written here. Yeah, so this is the circuit that is doing summation. It's doing summation. So it's supposed to give us correct summation. But you see, when they summed 2 and 2, the result is 5. So when it asserts, to confirm this, confirms the main. So x plus y, where this is x and this is y. When it does the summation and gets that it's 5, and 5 is not equal to the right sum, then the test is supposed to fail. And so these are you write it at the top of that test. And look at the earlier one, proving the same circuit, x plus y. So several instances have been given. The first one is x plus y, where x is 2 and y is 2. The right sum has been reached. And then the second instance is 0 and 1, right sum. Then 1 and 0, the right sum. So this test is supposed to pass. But the test number 2 is supposed to fail. And so a test that fails, this is how you write it at the top. That was just to emphasize so that you know how a test is supposed to be written. Of course, you can read many of these, a lot of these. Like you see here, the test here should fail. The test here should fail. And what the main function is, you just come back and look at the main function. So the main function here, is it this? It's saying A plus B should be equal to B plus A. So you come and check whether that is a correct thing. And if it's not, then the proof is supposed to, oh, this also a test. Oh, this also, it's not a main, this also a test. I thought it was main. But these are what you call the fuzz tests. The fuzz tests. Now, so that is how you show if a test is bound to pass or fail. And many other things you can read inside this Noir documentation. But I just wanted to emphasize on the issue of tests so that when you bring them to Merkle tree, not this. So the only part we were learning from that is this upper bit. And that if you're giving values, supposing it was summation, then those two values should add the expected sum. And if they don't, then that test is supposed to fail. And when it fails, I've already shown you how you're supposed to write a test that you expect to fail. Now, sometimes we include, most of the times, we include tests that pass and tests that fail, just to be sure that our circuit is compiling in the right way, that it's able to tell us if our test is correct, and if our test is wrong, that test must fail. That is just to confirm. Now, so in our test here, the leaves have been defined. The leaves have been defined. You have leaf 0, leaf 1, leaf 2, leaf 3, all the way up to leaf 7. So these are 8 leaves. So that is 11, 12, 33. I've just used these numbers not because of any other reason, but it's because they're easy to identify. Like 11 is easier to identify than 12, than 13, than 14. And even 22 is easier to identify than 21, than 23, and so on. So these numbers, I did not use them that because they are divisors of each other, or that to get one, you have to multiply the other by 2. No, that was not the reason. The reason is because they're easy for me to identify. Now, so we want to compute level 1. So we are pairing these leaves. We are pairing these leaves and doing hashes on them. We are pairing the leaves and doing hashes on them using the partisan hash. So you can pair leaf 0 and leaf 1, and you call this hash, partisan hash, leaf 0 and leaf 1. And this will be, we can call them, we can call F1 and F2, now F0 and F1 to be the children of this first child of the roots. Let me just share the diagram I had drawn so that then we come back here. Let me just share the diagram we had looked at earlier. Let me share that diagram again. You look at it, and then we come back and look at that proof. There's this diagram I had shared earlier of the Merkle tree. The Merkle tree, remember we had this root, and out of this root we have this shell. Now, then the leaves. So when you combine these two leaves and hash them, that's what you get here. The hash of H1 and H2. And when you combine these other two leaves, H3 and H4, then you get the hash of H3 and H4. So that's what we are doing. So in our case, we have the leaves, 8 leaves, and they're labeled leaf 0, leaf 1, leaf 2, leaf 3, leaf 4, all the way up to leaf 7. So you're pairing them. Pair this, and then you hash. Pair this and hash, and so on as you proceed. So that is what I was just discussing in the proof. So this is what I was discussing. Now when you pair leaf 1 and leaf 0, the node will then be leaf 11, will be 11, the 11 one. So let 11 be 11 not, let 11 not be the partisan hash of leaf 1 and leaf 0. And then what about 11 1, 11 subset 1, subscript 1. So that one you are hashing F2 and F3, leaf F3 and leaf F2. Then you hash leaf F4 and F5, all the way up to F6 and F7. So you are done with the 11 not 11 1, 11 underscore 2, 11 underscore 3. Then you come to now computing level 2. And level 2 you are doing for 12 underscore 0. And so you then, this is what you obtained from the, you obtained 11 not 11 underscore 0, 11 underscore 1, 11 underscore 2, 11 underscore. So these are then what you pair. So you would pair 11 underscore 0 and 11 underscore 1. And then it is pair 11 underscore 2 and 11 underscore 3. So doing that, as you proceed, you now come to the final one. You can see you have only 2. You have only 12 underscore 0 and 12 underscore 1. So this is what is then supposed to give you the root. This is what is supposed to give you the root. If we would still be having more, then we would have taken longer to reach the root, but this time we've already reached the root, and so that is where we stop. Then we come to level 5. Step 5, so we'll just be building the proof. We now build the proof for F naught, leaf 0, the proof for leaf 0, and it will be index to binary, index to binary. This is just a binary 0, 0, 0. Then let leaf F1, so F1, 11, 1, and 12, 1 underscore be siblings. So that is now the root. The root now you are following up to the root. The first root I'm referring to, R-O-U-T-E. R-O-U-T-E, the root. And the other one is R-O-O-T. So the root you're following to go to the root is F1, then is 11 underscore 1, then 12 underscore. So those are the siblings or the path. You can call it the path or the root. The word path, I think, is okay because the root will confuse because you have two roots. But one of the root means the path you're following. Step 6, you call the circuit, let the index be 0, and let the result be main, where main has if no index and root. And then step 7, you confirm it worked. When you confirm it worked, use the assert. Assert is what confirms that what you've done worked, is correct. So once you do that, you can say nago compile and see whether it runs. No, it did not work. Oh, I wrote Mago. I wrote Mago instead of Nago. It's a Nago. It's only that M and N are together, so it's supposed to be Nago compile. Nago compile. Yes, it's a successful run. So it means our circuit therefore is correct, our proof is correct. So you can do Nago test just to confirm that our tests are also correct. And you may want to, if you want to generate a witness, you can say Nago execute. Okay. It says it was unable to deserialize inputs. The value passed for parameters index is invalid. So that means we need to put values inside here. Inside here, we need to put values. So it has just given us where to input values. So it's just a bonus now to input values that would work. So that's what we will do. Once you do that, it will then work. And when it works, it will then give you it will give you the witness. That's how we do. We want to get a witness. So you can do that up to Nago proof. And of course, Nago proof is not that we're using BB proof, verify, and even write solidity verifier, and so on. We've been doing in other classes. They're still the same commands. The same commands. The only thing you need to know is a circuit compiling. If it compiles, then you proceed with the other commands. You can even write auto-generate. You can automate proofs by scripts, using scripts. build.sh, you can use that to automate proofs so that when you run, it runs automatically. You don't need to input the commands all the time. To put the commands all the time. So once you've written that build.sh, you put commands. You can run. You can have keygen.sh to automatically generate keys for you. Go up to automating generation of solidity verifier, which we then use as our contract later in deployment and so on. Now, so when I shared that proof or the VS Code, you've seen the following. You've seen the leaf. Of course, it's hashed data so that you cannot identify it. It's hashed. Of course, we took L leaf 0 not, a leaf not 0 and leaf 1. We hashed 2 and 3 hashed, 3 and 4 hashed, 5 and 6, and so on. So we hashed those. Then after that, we came and hashed. So everything there is hashed. So, and again, that is just to hide the data for security reasons, making it secret. Then we also saw the proof, and the proof will be the sibling nodes. And then index is leaf position. And then the root will be the expected root. For instance, we had hash, this is hash 2. So we hashed A and B and so on. But next we'll be looking at this, looking at hash 2 function. So just to end our class, I want you to do the following just as practice. Want to write a Merkle proof for airdrop example. So this is what I want you to do. These are what you'll be doing. So publish a Merkle root for eligible address. Claimants, I should provide the following. Claimants should provide their address, which is hashed, and then Merkle proof. And they will should also provide the root. So that is the proof you're writing the circuit. So this circuit, the claimant should provide this. And then the Noir circuit that you've written will verify the proof without revealing the list of the members who attained airdrops or who are supposed to be given airdrops. So you should not reveal their details. But they are supposed to give, those members will be giving hashed data, be giving their address, which are hashed, giving Merkle proof, they're also giving the root. So that is one thing that I want you to do as an assignment. I just try to write that Merkle proof. Of course, you can check, it's not something that is very new, something that has been written before. So you can check documentations and just to see what others have written and see if you can internalize the same and write. Remember, this we're just looking at Merkle proof that shows membership, proving membership. So that will prove even voting, secret voting, and so on. So just, if you get any of them, you will look at it and then generalize. What are other applications of this? Other than airdrop that I've mentioned, the other one would be membership proofs. Prove you're in a group. The other one would be anonymous voting. proving that somebody is qualified to vote without indicating or revealing their identity. And then the other one where we can apply that is private access control. So you prove rights without disclosing all members. Now, once you've written that circuit for airdrop, you can pick any of this and again write a circuit for any of this. Just as part of exercise. Is this a continuation? This is another exercise you can do. Given a Merkle tree of 8 addresses, prove your address is included. Prove that your address is one of the 8 addresses. And as you do that, ensure that you don't reveal your address. So the inputs in this case will be leaf, roof, index, and root, as we saw earlier. So you would then your leaf, to ensure that your address, which is the leaf in this case, to ensure that it's private. You don't include the word pub. That will just mean that it's private. Now, to assist you do the above exercises, you can consult these resources. You can consult Noir Merkle example. If it exists, they may have changed. You see, they update their examples all the time. So we have examples which sometimes become outdated and then they are changed and so on. Also, other documents that have Merkle proofs, you can look at them and then also look at Poseidon hash in Noir, so you understand how it works and you understand how it's used in Noir circuits and how to use it. Okay, if there is no question, unless somebody has a question, but if there is none, I can end at that. But as we end, you should discuss, just with yourself or with your friends, to discuss how to use Merkle proofs in your privacy preserving apps. You can discuss that when we meet in our next class. We start from there, maybe we get to hear 2 or 3 views of how Merkle proofs can be used in our privacy preserving apps. Okay, let's end it there. Thank you.